Hello and welcome to this special edition of In Depth on Rajya Sabha Television. I'm Smriti Rastogi. The world will today see the first ever true image of a black hole. There is much excitement about the revelation, not just among the scientific community but also among the ordinary lay public. For what will be revealed will be the shape of the mysterious region of the space-time fabric that has fueled human imagination and inspired numerous sci-fi movies and literature for generations. The landmark moment for science and technology has been made possible by the Event Horizon Telescope, that is actually an array of telescopes spread out across the Earth. The Event Horizon Telescope project has imaged two supermassive black holes with the largest apparent event horizons. These are Sagittarius A star at the center of the Milky Way and M87 in the center of the Virgo A galaxy. To really capture a direct image of a black hole, or at least the shadow of one, requires serious collaborative engineering. Today, scientists will release images of two supermassive black holes at a press conference simultaneously in Shanghai, Taipei, Tokyo, Washington, Brussels and Santiago. We are getting you a special coverage on this. But before we begin the show, let me introduce our eminent panelists who are here with us to discuss this entire event. TV Venkateshwaran, scientist, and Professor Patrick Dasgupta, Department of Physics and Astrophysics. And also Ms. Prajwal Shastri, astrophysicist. Thank you everyone for joining us on the show. We welcome you to the very important discussion which we are having today on the black hole. TV sir, I'll come to you first. At least for the last 100 years, people have been speculating about the existence, about the presence of black holes. Now, with the first image of these two supermassive black holes which are going to be released today, how big it is an achievement for the scientific community?
Okay, in science or generally in when we talk about something to accept as true, usually, for example, in Indian philosophy, we'll say that there are three kinds of pramana.
Right.
There is a pratyaksha pramana, that if I see that I am holding a mobile on my hand, I'm sure it is there. Okay, the second is anumana. Suppose you are not seeing me, I'm inside a room, but I'm talking. You can clearly know that I'm talking over a telephone, so you'll assume that I'm holding a mobile phone. So, it's anumana. Then third is, of course, what is called as agama. In science, we don't accept agama evidence. We accept only pratyaksha and anumana.
Right.
One type of anumana is called attapati, which means it's a logical implication. Like, for example, if I tell you that there is a number, if I divide that by 2, I get a reminder. Then immediately you will know that that number is an odd number, right? Yeah. So, but you don't know what the number is. Still, you will make a guess about that because of the logical implication. Till now, all the evidence that we have for black hole is a logical implication.
Right.
We don't have any direct evidence. The moment you have direct evidence, our confidence on our theories, our ideas, our speculation increases tremendously. So, this picture would bring a reality to black holes in a tremendous way than what it was earlier.
Coming to you, Professor Patrick Dasgupta, all this while, the images which we have been seeing from, which we have been getting from NASA and other scientific organizations, they were the clear illustrations. They were only illustrations by the artist and based on the mathematical predictions. Now, we want to understand what is actually a black hole and why we can't see it.
Correct. So, black hole is essentially such a compact object that if you naively use Newton's theory of gravity and try to estimate what is the escape velocity from the surface of such a compact object, the escape velocity turns out to be greater than the speed of light. And theory of relativity, Einstein's theory of special relativity, that itself implies that no object can ever travel faster than the speed of light.
Absolutely.
And therefore, if you have compressed an object to such a small size that the escape velocity from the surface of that object turns out to be greater than the speed of light, that means nothing can escape such a surface. So, using Newtonian gravity itself, you can infer that there will be such dense and compact objects from which even light can not escape, and therefore they will never be visible. Although Einstein's general theory of relativity says something more, and that is that once you compress an object, any object, beyond a particular radius called the Schwarzschild radius, for example, for the sun, the Schwarzschild radius is only 3 kilometers, while the actual radius of the sun is 6.96 into 10 to the power 5 kilometers. The sun is not a black hole, but because it's much larger than the Schwarzschild radius of 3 kilometers. But if you were to compress sun to a radius less than 3 kilometers, then general relativity predicts that entire matter, it will inexorably will accelerate towards a single point.
Single point.
So the entire matter will just go into a single point, making the density infinite, and all geometrical entities associated with gravity infinite. So such a point is called singularity, and general relativity predicts that there is a mathematical surface hiding that point of singularity, and this mathematical surface is called event horizon, whose speciality is any event that happens beneath this mathematical surface called the event horizon that can never be seen because even light can't escape. And even if I have the most powerful rocket at my disposal, once I enter the event horizon, no matter with what full throttle I fire my rockets, I can never come out of the event horizon.
Right. On that note, I'll also speak to Ms. Prajwal Shastri. Ma'am, I would like to ask you, what is the basic difference between a supermassive black hole and an astrophysical black hole?
There is no difference. A supermassive black hole is an astrophysical black hole. A supermassive black hole is special in certain ways. It is special because, first of all, its mass is more than 1 million times the mass of our sun. That's why we call them supermassive. We do know of black holes which are much smaller masses within the Milky Way. These are believed to be formed as a result of stellar death, basically,
right.
And they are something like 5 times to about 60 times the mass of our sun, maybe more, but we know of those which are about 5 times to about 60 times the mass of our sun. So they are known as stellar mass black holes because they are the result of stellar death. Now, you would expect that there would be a gradual increase in masses of black holes that we know. But as it turns out, strangely enough, we know of supermassive black holes, which are 1 million times the mass of our sun at least, and more, even 1 billion times the mass of our sun. And these are found in distant galaxies, in the centers of distant galaxies. And then we have the stellar mass black holes, which I mentioned earlier. But in between, we don't know of that many black holes. People have worked hard and found black holes that are, instead of being 1 million, they are 100,000 times the mass of our sun. But in the range of about 1,000 to 10,000, we don't know. We don't have evidence for black holes.
Right.
So basically, people talk about the stellar mass black holes that are a result of stellar death, the intermediate mass black holes, which are mostly missing, and the supermassive black holes for which there's plenty of evidence and which occur in the middle of distant galaxies and in, of course, our own Milky Way.
And coming to you, Mr. Professor Dasgupta, how do we know that Sagittarius A star and M87 are supermassive black holes?
So let's first come to the black hole which is supermassive at the heart of our own Milky Way galaxy. which is called the Sagittarius A star source. What was done was from 1995 to about 2004, astronomers, they monitored the motion of stars which were orbiting very close to the center of our Milky Way galaxy. And there were some stars which were going in circular orbits, some with highly elliptical, that means highly eccentric orbits. And from the orbital motion, using standard Kepler's law, you can estimate what is the mass that was keeping the objects in circle or in elliptical orbits around a small point. So you could estimate the mass, and mass turned out to be something in excess of 4 times million times sun's mass. So the mass part was measured through the orbital motion of many stars over a period of almost 10 years. Now, several of these eccentric orbit stars, they found that the smaller of the radius, that is the closest distance to the point around which they were orbiting, was so tiny. It was of the order of 6,000 or maybe slightly over 24 million kilometers. So it was so tiny. So therefore, imagine having an extended source whose mass is in excess of 4 million solar masses,
right,
and its radius of the order of something like more than 12 million kilometers, meant that it could be nothing but a black hole, because from the stellar evolution theories you could prove that you cannot have stars whose mass is more than 1,000 times sun's mass, because there are instabilities like electron positron pair creation instability, so they will just explode. And having an extended object whose mass is more than 4 times 10 to the power 6, that is more than 4 million solar mass, and having a size of only about 12 million kilometers, you cannot have any extended object. The only object that from your theoretical studies, namely general relativity and standard astrophysics, you predict is that of a black hole.
Right.
So that is why it was essentially measurement of orbital dynamics of stars around the galactic center, and using fairly well tested rules of general relativity and standard astrophysics, you could indirectly say that there is a supermassive black hole.
Mr. TV, I'll take your comments after this very bit of information that according to the scientists, the Event Horizon Telescope, we are talking about the Event Horizon Telescope, that has collected image data of 2 supermassive black holes, Sagittarius A star and M87. The Sagittarius A star is a supermassive black hole, which we have been discussing, that is at the center of our Milky Way galaxy. It's 25,000 light years away from the Earth. The supermassive black hole is 4.3 million solar masses. Simply put, it has a mass equivalent to or weighs about 4.3 million of our suns. Sagittarius A star is the only black hole whose mass has been measured directly by observing the full orbit of a circling star. Meanwhile, the black hole at the center of M87, which is a galaxy in the constellation Virgo, has a mass equivalent to 7 billion suns, or 1,700 times bigger than our own black hole. M87 is remarkable for producing a dramatic jet of particles streaming some 5,000 light years into intergalactic space. And let us also understand what exactly is a black hole.
A black hole is a region in space where the pulling force of gravity is so strong that light cannot pass through it. The pull of gravity is strong in black holes because matter has been pressed into a tiny space. This compression can take place at the end of a star's life. Because no light can escape black holes, they are invisible. Some black holes are a result of dying stars. Black holes can appear in a range of sizes, but there are three main types. The smallest ones are known as primordial black holes. Scientists believe this type of black hole is as small as a single atom, but with the mass of a large mountain. Primordial black holes are thought to have formed in the early universe soon after the Big Bang. The most common type of medium-sized black holes are called stellar. The mass of a stellar black hole can be up to 20 times greater than the mass of the Sun and can fit inside a ball with a diameter of about 10 miles. Dozens of stellar mass holes may exist within the Milky Way galaxy. Stellar black holes form when the center of a very massive star collapses in upon itself. This collapse also causes a supernova or an exploding star that blasts part of the star into space. The largest black holes are called supermassive. These black holes have masses greater than 1 million suns combined and would fit inside a ball with a diameter about the size of the solar system. Scientific evidence suggests that every large galaxy contains a supermassive black hole at its center. The supermassive black hole at the center of the Milky Way galaxy is called Sagittarius A star. It has a mass equal to about 4 million suns and would fit inside a ball with a diameter about the size of the Sun. Scientists believe supermassive black holes formed at the same time as the galaxy they are in. The size of the supermassive black hole is related to the size and mass of the galaxy it is in. A black hole cannot be seen because of the strong gravity that is pulling all of the light into its center. However, scientists can see the effects of its gravity on the stars and gases around it. If a star is orbiting a certain point in space, scientists can study the star's motion to find out if it is orbiting a black hole. When a black hole and a star are orbiting close together, high energy light is produced. Scientific instruments can see this high energy light. A black hole's gravity can sometimes be strong enough to pull off the outer gases of the star and grow a disk around itself called the accretion disk. As gas from the accretion disk spirals into the black hole, the gas heats to very high temperatures and releases X-ray light in all directions. NASA telescopes can measure these X-ray light, and astronomers use this information to learn more about the properties of a black hole. There are so many black holes in the universe that it is impossible to count them, but none of the universe's known black holes are close enough to pose any danger to Earth. Black holes follow the laws of gravity just like other objects in space. The orbit of a black hole would have to be very close to the solar system to affect Earth, which is not likely. If a black hole with the same mass as the Sun were to replace the Sun, Earth would not fall in. The black hole with the same mass as the Sun would keep the same gravity as the Sun. The planets would then still orbit the black hole as they orbit the Sun now. The Milky Way galaxy contains some 100 billion stars. Roughly 1 out of every 1,000 stars that form is massive enough to become a black hole. Therefore, our galaxy must harbor some 100 million stellar mass black holes. Most of these are invisible and only about a dozen have been identified. The nearest one is some 1600 light years away from Earth. In the region of the universe visible from Earth, there are perhaps 100 billion galaxies. Each one has about 100 million stellar mass black holes, and a new stellar mass black hole is born in a supernova every second. Supermassive black holes are 1 million to 1 billion times more massive than our Sun and are found in the centers of galaxies. Most galaxies, and maybe all of them, harbor such a black hole. So, in our region of the universe, there are some 100 billion supermassive black holes. The nearest one resides in the center of our Milky Way galaxy, 28,000 light years away.
So, we were discussing about the black holes. That Sagittarius A star and M87 are the supermassive black holes. Stevie sir, your take.
Yeah, let's look at this point. This is what I was pointing out. See, we infer that there is a supermassive black hole at the center of our Milky Way by looking at other objects. We are not looking at the black hole itself.
Right.
So we don't know. No,
Yeah.
I mean it's a kind of an informed guess. This is exactly what I was saying, that all the evidences we have today
Right.
are a kind of a logical inference.
Right.
Okay, very simple. Assume that you have a black cloth and you are covering the sun, so nobody can see the sun. But then you can see that in 88 days the Mercury is going around in one rotation near it, and it'll you can see Earth going around it in 1 year, and you will see Neptune going around it in 165 years. From this moment, you can't actually calculate what should be the mass of sun. And because Mercury is rotating here, you know that the sun is less than this size. From this, you make an inference that this much of mass is in this small area, right? So of course, in sun case, it's only a star. But when you are talking about the center of our galaxy or any other galaxy, you find that so much of mass is in a very, very short, a very, very small region. So its density should be really so high. You know, I mean, it can't be anything other than black hole. That's a kind of, logical implication that one is going through. This discovery is going to be a landmark because we might have a very direct evidence which will give a tremendous confidence to our own theories. Yeah, that's I think an important point to underline.
Going to Ms. Prajwala Shastri, how do we know that there is a black hole exists, but we can't see it?
So, if we're talking about the giant black holes in galaxies like Messier 87, astrophysicists speculated that there were supermassive black holes in such objects because of the kind of power that we see come out of these galaxies. So as TVV was saying, this is basically circumstantial evidence. So the most energetic phenomena that we know in the universe have been associated with such galaxies. So not every galaxy, but about a small fraction of galaxies emit a lot of power from their centers, and they also squirt out their jets of plasma, as was already mentioned, which reach out into intergalactic space. And the only way we know of creating such phenomena is through the harnessing of gravitational energy around a supermassive black hole. Within the galaxy, yes, again, we have not actually seen the black hole itself. But as Patrick Dasgupta mentioned, we have tracked stars into elliptical orbits. So they're zipping around a dark point, and that must harbor a dark object with a mass which is in a very small volume, and so therefore there must be a black hole there. What we're hoping to do with the Event Horizon Telescope is something slightly different. So the hope is that there is light coming out of the region around the giant black hole in the center of our Milky Way. And we expect that when this light is coming from material which is very, very close to the black hole, instead of it just coming straight at us, because black holes warp space-time, that is what general relativity predicts. Warping of space-time near the giant black hole means that light rays will bend. And if light rays bend, then we will see a very predicted pattern of light around the black hole. In other words, we will be able to see the shadow of the black hole. So we will still not be able to see the black hole itself. That is not possible because by definition, a black hole cannot be seen. But we hope to see the shadow of the black hole, right. And we hope to get a sharp enough image with the Event Horizon Telescope that will clearly and unambiguously show that shadow.
Right. There, Ms. Prajwala Shastri telling us about the salient features about the Event Horizon Telescope, which is a network of radio telescopes spread across 5 continents that is collectively operating as a single instrument. Coming to you, TV sir, what is inside the Event Horizon and why is it a one-way gateway?
Event horizon is a region in space where, where you can say that, for example, the light will not escape out of it. So if the light cannot escape out of it, it means that nothing can come out of it. So if something goes inside, if it has to come back, which means that it should, first of all, if it is going inside, it will be going in one particular momentum, so momentum has to stop and then reverse and come back, which is not going to be possible, because even if you have the velocity of light, the escape velocity will not be enough for you to come out.
Right.
So that's why it's called as event horizon. Actually, it's called as event horizon because no event which is happening inside, you can ever observe it from outside. You can watch all the event that is happening up to that event horizon, but not beyond it.
Right.
So you cannot know what is happening inside. That's it's a very, very important feature. For example, if I look at me, you can talk about many things about me. For example, my weight, my age,
Absolutely.
my height. You can talk about right now my body temperature. You can talk about my blood pressure. Maybe right now my sugar level. You can talk about so many things about me. But for a black hole, you can only talk about only three characteristics. Its mass, its size, that is the event horizon size, and third, its charge on the surface. Okay, so which means other than these three, nothing else you can talk about a black hole. What is inside, whether they exist in terms of particles or atoms, no, nothing. You can talk about nothing what is inside. So no event you can know. That's why it's called as the event horizon. So that's a horizon beyond which you cannot see. In the same fashion, for example, if you are standing on the edge of a sea, you see a horizon beyond which you are not able to see from that point the different parts of the earth. Earth exists, but you cannot see. That's why we call it as a event horizon, beyond which you cannot see what is inside.
Coming to you, Mr. Das Gupta, how many black holes are there in the universe?
In fact, all major galaxies in the universe which have been monitored appears to have a black hole, supermassive black hole at the center. So the universe consists of elliptical galaxies, which are big galaxies thought to have formed by merging of two or more spiral galaxies. So there are spiral galaxies which have magnificent spiral arms along which very new and bright stars are formed. Similarly, there are disrupted galaxies. They have got disrupted because of the gravitational forces of other galaxies, like small Magellanic Cloud and large Magellanic Cloud, which are essentially not very far from our Milky Way galaxies. They are a little bit torn apart. They are disturbed galaxies.
Right.
And there are also smaller galaxies called dwarf ellipticals, whose mass wise they are 1/100th of our Milky Way galaxies. Most of the spiral galaxies and elliptical galaxies, which are big, they have been observed to have supermassive black hole at their centers. So therefore, there are as many supermassive black holes as there are spiral galaxies and elliptical galaxies.
TV sir, if we talk about the research, you were telling us about the three basic characteristics about a black hole. So is there any research about the age, about the origins of a black hole?
Okay, as far as the origins of black holes are concerned, there are three types broadly. One can say that as far as the physics we know, it can form. One is the black holes which perhaps got formed when the universe was formed. That is what we call as the Big Bang event. You know, immediately after the Big Bang event, some black holes could have formed, which is called as primordial black holes. We don't know so much about it. In fact, I would say that we have not even discovered one such primordial black holes as of now. I mean, people are searching for it. I mean, there are enormous work on that area, but it's a theoretical speculation as of now. The second is a big surprise which has come in the last few decades is the centers of galaxy having supermassive black holes. Like Dr. Prajwal Sastry was mentioning, they are of masses of million times our sun.
Right.
You know, I mean, not just 1 ton, 2 sun, 3 sun, but put millions of suns together. That's a kind of huge mass they have. The third is some stars. When they die, I mean, in a figurative sense, they will die as a black hole.
Right.
I mean, if the stars are having huge masses, something like about 20 times the mass of sun, most likely that star will end up as a black hole.
Right.
So they are called as stellar black holes. There are three kinds of varieties. We have indirect evidence for the second one and the third one. In fact, Dr. Patrick Dasgupta is one person who has been working on primordial black holes. Maybe you can say a few words on this.
Yes, sir. Your comments.
Okay, so primordial black holes, as TVB just now mentioned, were formed very early on. I mean, when the universe was very dense and very hot, so that within the horizon of small region, the fluctuation of the matter was so large that the mass within the Hubble radius at that time satisfied the Schwarzschild criteria. The size was small, mass is very large, and it collapsed to form tiny primordial black holes. Now, the primordial black holes, because they are tiny, the Hawking temperature, as you know, Stephen Hawking predicted that black holes, when you address the region around the event horizon from the point of view of quantum physics, then the event horizon actually appears like a black body emitting thermal radiation.
Right.
Unfortunately, the temperature of the event horizon from Hawking's calculation turned out to be inversely proportional to the mass of the black hole. So, in other words, if you have a black hole of mass like Sun, the temperature of the event horizon is, according to Hawking's calculation, is 10 raised to minus 7 degree Kelvin, which is too small to ever detect such Hawking radiation. On the other hand, if you have a primordial black hole whose mass is, let's say, 10 raised to 15 grams,
Right.
much less compared to the mass of the Sun. Sun's mass is 2 into 10 raised to 33 grams. So if you take a black hole whose mass is about 10 raised to 15 grams, then its Hawking temperature would be of the order of few million electron volt in energy units.
Right.
That means it will be emitting energy at that surfaces, the temperature is of the order of 10 raised to 10 to 10 raised to 11 degree Kelvin. So they will be essentially emitting X-rays and gamma rays. So one of the work which was done by many cosmic ray physicists, including the cosmic ray physicists of
Right.
Tata Institute,
Right.
was to check whether there are some gamma ray bursts happening over a short time scale, because such black hole will just evaporate away, emitting X-rays and gamma rays. And so far, no such direct evidence of an evaporating primordial black hole has been measured.
Absolutely. TV sir, I'm sure that most of our viewers will be having this question on their mind, a very interesting one. Is a black hole a threat to the Earth?
Yeah, a lot of people have this fear that maybe one black hole will just fly past us and maybe eat the whole Earth and then go away. That's not going to happen. I mean, in a sense that the chances of such a thing happening is like so remote. So I don't think we should fear black holes, but rather be fascinated with it.
What about the Indian connection?
Yeah, there is a very interesting Indian connection to black holes. Maybe I'll say one episode related to one person called Vishveshwara. Okay.
All right.
I mean,
TV sir, I'll have to intervene you
I
there
think-
because we have a live event there which we have been always talking about, and an important one.
Yes.
There, we'll
We've
take
never
you there
actually seen
and let's listen
the
in.
event horizon, that point of no return after which nothing, not even light, can escape a black hole. How did we get here? Through the imagination and dedication of scientists around the world, willing to collaborate to achieve a huge goal. Through a large pool of international facilities, and through long-term financial commitments from NSF and other funders willing to take a risk in pursuit of an enormous potential payoff. Without international collaboration among facilities, the contributions of dozens of scientists and engineers, and sustained funding, the Event Horizon project would have been impossible. No single telescope on Earth has the sharpness to create an unblurred, definitive image of a black hole's event horizon. So, this team did what all good researchers do. They innovated. More than 5 decades ago, other NSF-funded researchers helped lead the development of very long baseline interferometry, which links telescopes computationally to increase their capabilities. This team took that concept to a global scale, connecting telescopes to create a virtual array the size of the Earth itself. This was a Herculean task, one that involved overcoming numerous technical difficulties. It was an endeavor so remarkable that NSF has invested $28 million in more than a decade, joined by many other organizations in our support, as these researchers shaped their idea into reality. I believe what you're about to see will demonstrate an imprint on people's memories. The Event Horizon Project shows the power of collaboration, convergence, and shared resources, allowing us to tackle the universe's biggest mysteries. And now I'm going to hand over this to our distinguished panel, starting with Dr. Shep Doleman, EHT's director.
Thank you, assembled guests, black hole enthusiasts. Black holes are the most mysterious objects in the universe. They're cloaked by an event horizon where their gravity prevents even light from escaping. And yet, the matter that falls onto the event horizon is superheated, so that before it passes through, it shines very, very brightly. We now believe that supermassive black holes, millions, even billions of times the mass of our sun, exist in the centers of most galaxies. And because they are so small, though, we've never seen one. There, though, they can outshine the combined starlight of all the constituent stars in those galaxies. The best idea we have of what they can look like come from simulations like this. The infalling gas that's superheated lights up a ring of light where photons orbit the black hole. And interior to that is a dark patch where the event horizon itself prevents light from escaping. The Event Horizon Telescope project is dedicated to the idea that we can make an image of this black hole, that we can set a ruler across this shadow feature, measure the photon ring, and test Einstein's theory where they might break down. It also will allow us access to a region of the universe where we can study precisely the energetics and how black holes dominate the cores of galaxies. To do this, we worked for over a decade to link telescopes around the globe to make an Earth-sized virtual dish. The aim is to, the Event Horizon Telescope achieves the highest angular resolution possible from the surface of the Earth. It's the equivalent of being able to read the date on a quarter in Los Angeles when we're standing here in Washington, D.C. In April of 2017, all the dishes in the Event Horizon Telescope swiveled, turned, and stared at a galaxy 55 million light years away. It's called Messier 87 or M87. And there's a supermassive black hole at its core. And we are delighted to be able to report to you today that we have seen what we thought was unseeable. We have seen and taken a picture of a black hole. Here it is. This is a remarkable achievement. What you're seeing here is the last photon orbit. What you are seeing is evidence of an event horizon. By laying a ruler across this black hole, we now have visual evidence for a black hole. We now know that a black hole that weighs 6.5 billion times what our sun does exists in the center of M87. And this is the strongest evidence that we have to date for the existence of black holes. And it is also consistent, the shape of this shadow, to the precision of our measurements with Einstein's predictions. The bright patch in the south that you see, tells us that material moving around the black hole is moving at light speeds, which is also consistent with our simulations and predictions. And this image forges a clear link now between supermassive black holes and the engines of bright galaxies. We now know clearly that black holes drive large-scale structure in the universe from their home in these galaxies. And we now have an entirely new way of studying general relativity in black holes that we never had before. And as with all great discoveries, this is just the beginning. So imaging a black hole doesn't come easily. I can tell you that from personal experience, as can many people here in the audience. It's required long-term developments, a committed team, but it also required some very interesting cosmic coincidences. Take, for example, the maelstrom you see before you, like the hot gas swirling around the black hole. A photon has to leave from close to the event horizon, travel through the hot gas in falling to the black hole, and light rays of a millimeter wavelength, radio waves, can make that journey. Not all of them can. Then that radio wave has to propagate 60,000 years through the M87 galaxy, and then another 55 million years through intergalactic space. And then it winds up in the Earth's atmosphere, where its greatest enemy, the greatest danger, is that it will be absorbed by water vapor in our own atmosphere. So the Event Horizon Telescope uses telescopes at high dry sites so that we can see the photons that have traveled to us so far. So far, so good. We have the photons. But the M87 shadow is very, very small compared to the galaxy that surrounds it. So in order to see it, we needed to build a telescope as large as the Earth itself, given the wavelength of light we were trying to observe. And to do that, we use a technique called very long baseline interferometry, which you can see a schematic of here. Radio waves from the black hole hit radio telescopes, where they're recorded with the precision of atomic clocks that lose only 1 second every 10 million years. When you've registered these radio waves so precisely, you can then store them on hard disk drives, send them to a central facility where they can be combined precisely. It's exactly the same way that a mirror used at an optical telescope reflects light perfectly and in synchronicity to a single focus. And when we do this, we can synthesize a telescope that has the resolving power as though we had one the size of the distance between these telescopes, truly turning the Earth into a virtual telescope. All the sites that we used can be seen here. We have telescopes from Hawaii to Arizona to Mexico to Chile to the South Pole and Spain. But even this broad global network is not enough by itself to make an image. You can think of them as being silvered spots on a large global mirror. The key is that the Earth turns. During a night of observing, we are able to sweep out more baselines, more coverage of this virtual mirror to make our image. So on the left, you'll see the Earth turning. Every pair of telescopes provides us with one point on the center panel, which fills in the Earth-sized virtual lens. And on the right, you see the evolving image. The more and more data we get, the more we fill in this virtual mirror, the sharper our view of the black hole becomes, until you wind up seeing what we have as the final image there. So we've taken advantage of a cosmic opportunity. It's remarkable when you think about it. Light that left near the event horizon, traveled all the way through intergalactic space. It hit our telescopes. The Earth just happens to be the right size. So we get resolving power so that we can see the black hole in M87, whose mass and distance let us observe it. And then the Earth turns to fill in our mirror so that we can make this image. It's truly remarkable. It's almost humbling in a certain way. Now, we are 4 members of a large collaboration, and it is our distinct honor to be here to represent that collaboration. We are 200 members strong, we have 60 institutes, and we are working in over 20 countries and regions. We consider ourselves really to be explorers. Through international cooperation and innovation, we've exposed part of the universe that we thought was invisible to us before. It's our responsibility now to report these findings, and we're doing that today to the National Science Foundation, to our funding agencies, international and foundations, and to all people who support pioneering research, and also to the taxpayers. Nature has conspired to let us see something that we thought was invisible. This is a long-sought goal for us, and we find it tremendous, and we hope that you will be inspired by it too. Thank you, and now let me introduce Dan Maroney, who's literally gone to the ends of the Earth to collect some of the data that we've seen here today.
Thanks, Chip. So, oh, there we go. So the heart of our measurement is, of course, the EHT array. It would have been an expensive, enormous undertaking to build a dedicated array just to do this experiment. So we didn't do that. Instead, we built an international partnership that allowed us to use submillimeter telescopes all over the world. In fact, we used basically all of the submillimeter telescopes in the world to make this measurement, one that none of them could have done on their own. When you take a heterogeneous collection of telescopes and build them into one giant telescope, it presents a lot of technical challenges. And so in the years leading up to our 2017 experiment, we went telescope by telescope all over the world, installing the specialized hardware we needed to do this. Most of the telescopes had detectors that we could use, but almost none of them had the atomic clocks we need, and certainly none of them had the very fast data recorders that we use. Some places we had to do even more. A good example of this is the ALMA telescope in Chile. It's a 66 telescope array. It's by far our most sensitive telescope, and its sensitivity is transformational for our experiment. But in order to use it, we didn't just need the basic hardware, we also needed a special piece of hardware that could sum the light from all the telescopes before we sent it to our recorders. This alone was a many-year project using an international collaboration of people from the EHT and also from the ALMA project. Another good example is the South Pole telescope. The South Pole is a special place in our array. It's so far south that it doubles the resolution of the EHT for sources it can see. But the SPT was designed to do a completely different kind of measurement. It studies the cosmic microwave background. And so its detectors are not the detectors we need. So in addition to bringing down an atomic clock and all the tens of crates of hardware that we needed, we had to build a special receiver that would detect the light the way we need it detected, special optics to relay the light to it, and install it and get it to work in the cold and sometimes harsh Antarctic environment.
So there, the most awaited moment in a landmark achievement for both the science and technology. Scientists have released the image of a supermassive black hole, that is M87. TV sir, to you. We knew that there is a black hole, but why this particular evidence is so important?
This evidence is so important in two counts. Number one, in my opinion, others can also come in. One, now you have a very direct evidence that there is a black hole over there because we have got a photograph. And
Right.
second, as in the press release they were mentioning, now you can actually put a scale over it, you can measure and see whether the predictions of Einstein's theory are correct to what extent. So you can now actually, I mean, Einstein's theories cannot be predicted on daily life that easily. I mean, you need this kind of extreme events, extreme situations. And now you have a facility, now you have a technology, now you have a capability of doing that. That will bring us to a new
Right.
step in physics. That's what I think.
Mr. Das Gupta, now we have got the first ever image of a black hole, M87. What will be the research ahead from here?
Yes, so M87 is an active galactic nuclei, which essentially means that although M87 is a large elliptical galaxy, but the center of the galaxy, the amount of energy that comes out from the center of the galaxy, it completely outshines the amount of energy that comes from the total number of stars within this huge, massive elliptical galaxy. That means the nucleus of this galaxy is much more active than the rest of the matter of the galaxy. And the astrophysical modeling, when they took the data, they found that the radio emission, the X-ray emission, in fact there is a jet coming out of the nucleus of the M87, and there is a flickering in the X-rays, the flickering in the high energy radiation that is coming out from the nucleus. From the time scale of flickering, we know that the region that is emitting radiation is very compact. The reason is that if the fluctuation happens within few hours, then the size that is emitting the radiation has to be less than speed of light into few hours time scale of fluctuation.
Right.
That itself tells us that the size of the object can be only of the order of, Schwarzschild radius of a 10 raised to power 10 solar mass object. And the actual estimated mass of the black hole, as it was pointed out in the press release, is 7 billion solar masses.
Right.
So now the mass has been precisely estimated from the observations that came out from the Event Horizon Telescope.
Right.
The further thing which can be done is by seeing the radiation pattern, one should be able to estimate that this black hole, does it rotate, does it have a spin angular momentum? Because as was already mentioned, the black holes are characterized by only three things. Mass of the black hole,
Right.
the spin angular momentum of the black hole, and the electric charge of the black hole.
Absolutely.
The spin of the black hole causes some dragging of frames called lens steering precession and geodetic precession, etc. So in principle, by looking at the radiation that is coming out from the region surrounding the event horizon, the detailed pattern, one should be able to estimate that apart from this 7 billion solar mass black hole, does this black hole, is it rotating? Because if there is a rotation of the black hole, then there are more astrophysical phenomena that can be
Aspects
possible.
to it, yeah.
For example, there is a mechanism which was suggested by Blandford and Najek, which says that if you have a rotating black hole immersed within a plasma that carries magnetic field, then the event horizon acts like a conductor placed, rotating conductor placed in magnetic field that would radiate in terms of jets. So, in other words, once one starts in detail analyzing the radiation pattern, one should be able to find out what kind of angular momentum resides within this black hole. That is one thing which otherwise is very difficult to fathom.
On that note, I'll also speak to Ms. Shastri. Ma'am, I would like to ask you that after the releasing of the image of M87, the supermassive black hole, what is the more use of this technology and what will be the impact on the human life?
The use of the technology is that this is more or less the sharpest image we've ever taken of the sky. So as it's like being able to, for example, see a mango-sized object on the moon sitting here on Earth, or it is like reading the newspaper that is in Delhi by me sitting here in Bengaluru. So this is the kind of sharpness this image has, and in that sense, it is a very important technological development, and it will have wide-ranging implications for astrophysics. That is one part of it. In terms of the conceptual development, I would say the role of astrophysics is really to tell us, to show us what is our place in the universe. And the more we learn about how fascinating the universe is, how big it is, how small the Earth is in comparison to all of these things, and how changing and dynamic everything is. I think that changes our perspective of how we evaluate our own situations, our own conflicts, our own barriers and boundaries, and all of those things.
And coming to you, TV sir, does it mean that there are no mysteries left?
Well, that's not actually correct. I'll also just add a word to Dr. Prajwal Sastry. See, one is it has an astrophysical use. Second is that now you have new tools to understand the universe. But the technology behind it also has lots of use for common public, in future. You look at 8 telescopes in different parts of the world and they have to work synchronously. That kind of precision technology it will be useful for developing future computations, future imaging technologies. Maybe tomorrow your new CAT scan may have some technology that has come out of this, which may not be seen. Okay, so that's, I think, something that we as ordinary people should understand, that these are not merely esoteric act. By this, we are actually making a human progress. That's, I think, one thing we should know. The question that you asked me, I mean, are there no mysteries? I mean, the universe is full of mysteries. We have got very interesting answer, but that means there is more questions to answer now, right? I mean, look at sun. Sun surface is roughly about 5,000 degree Kelvin. But look at the envelope surrounding sun, that is corona. That's about million degrees. How come the outside of sun is so hot? We still don't have a clear answer. There are so many mysteries in this world, in astrophysics, in physics, in biology, in life sciences, in so many areas, that it's a very, very fascinating thing to explore.
On that note, we'll have to wrap up our discussion here. Thank you so much, Mr. T.V. Venkateshwaran, and so much, Mr. Dasgupta, and thank you so much, Ms. Shastri, for joining us on this very interesting and fruitful discussion on the very interesting part of the space sciences, black holes. Remember, in a landmark moment for the science and technology today, the scientists have released the image of the supermassive black hole M87. On that note, we'll wrap up this show here. Thank you for watching. Namaskar.